Welcome! Welcome to the Plasma Physics course of TPFL. In the past module, we have derived the two-fluid dispersion relation. If you wanted the relation between the frequency and the wave number of the modes that are intrinsically present in a plasma, according to the two-fluid description. Now it's time to look more into details at what are these modes, what are the waves that are actually described by the two-fluid model. For this purpose, I will very briefly recall the two-fluid dispersion relation, and then I will show you that there are waves that are propagating both in the parallel and in the perpendicular direction to the equilibrium magnetic field. So to start, what is the equilibrium we are considering? We are considering a static equilibrium. Therefore, the equilibrium velocity of the plasma species is equal to 0. We are considering a plasma that is neutral, of course, in the equilibrium state, and therefore where the equilibrium electric field is equal to 0. And we will also consider equilibrium magnetic field that is uniform and static, and we will turn our coordinate system in such a way that the equilibrium magnetic field becomes parallel to the EZ vector. As we are considering the cold plasma dispersion relation, I just remind you that we will assume both equilibrium and perturbation of the temperature equal to 0. The linearization and Fourier mode analysis of the two fluid equations and Maxwell equations show us that n squared, the index of refraction, times k divided by k squared minus the identity dyad plus epsilon dot E1 is equal to 0, where epsilon is given by the sum of epsilon 0 over omega plus the identity dyad. And as we have seen in the past module, this can be written as introducing three functions, epsilon 1, epsilon 2, and epsilon 3, where epsilon 1 is equal to 1 plus the sum over all species, the plasma frequency divided by the cyclotron frequency. Just to remind you the definition of omega s, the cyclotron frequency, and of the plasma frequency. And epsilon 2 is given by minus the sum over all species of omega s divided by omega plasma frequency, and epsilon 3 is 1 minus. The intrinsic modes present in the system are the one for which the determinant of this matrix here is equal to 0. A few observations. Well, first of all, by looking at this dispersion relation, we can observe that the plasma seems to be an isotropic medium. The direction, the third direction, the z direction along the magnetic field is actually very different than what happens in the plane perpendicular to it. Well, let's give a look. Is this due to the presence of the equilibrium magnetic field? Well, let's take the limit of equilibrium magnetic field equal to 0, which implies that the cyclotron frequency is equal to 0. And this implies that epsilon 1, well, if omega s squared is equal to 0, epsilon 1 becomes equal to epsilon 3 and equal to 1 minus the sum over all species of omega plasma frequency square omega, while epsilon 2 being proportional to omega s becomes equal to 0. Well, the off-diagonal terms of epsilon therefore are equal to 0, and epsilon 1 becomes equal to epsilon 3, it means that epsilon is equal to epsilon 3 times the dyad matrix. In this case, plasma is an isotropic medium. Second observation that I would like to do. Well, let's look at our space x, y, z. We have that the magnetic field, equilibrium magnetic field, is in the direction of the z axis. Okay, we can turn the x and y axis in such a way that the k vector lies on the yz plane, and denoting theta as the angle between the z-axis and k, we can write k as the k in the y component along the y direction plus the component in the z direction. With this expression for k, we have that this term here, n square kk divided by k square minus the dyad plus epsilon becomes equal to minus n square I epsilon 2 0 0 n square sin theta cos theta n square sin theta cos theta, and for the last term n square sinus square of theta plus epsilon 3. What are the intrinsic modes present in our plasma? We will show that there are modes that are propagating parallel to the magnetic field. That means that the angle between the magnetic field and the k vector, the angle theta, is equal to 0, and modes that propagate in the direction perpendicular to the magnetic field, where theta is equal to pi over 2. We can start by analyzing the modes propagating parallel to the magnetic field. Is in the three-dimensional space a magnetic field that is in the z direction, and same thing for k. K which we wrote equal to k sin theta ey plus k cos theta ez. Okay, we will write equal to k ez. Basically, we will consider the case of theta equal to 0. In this case, the dispersion relation, the determinant of this matrix equal to 0. Well, what we can immediately notice is that there are two families of solution. In fact, the determinant of this matrix can be equal to 0 because epsilon 3 is equal to 0, or because the determinant of this 2 by 2 matrix is equal to 0. The first case is the case of epsilon 3 equal to 0, which means 1 minus the sum over all species of omega ps square over omega square equal to 0, which implies that omega square is equal to the sum over all species of their plasma frequency. And now, as the electron plasma frequency is much higher than the ion 1, this, to a good approximation, can be written as omega p electrons, omega plasma frequency for the electron square. What have we found? Omega square equal to omega plasma frequency square. These are the plasma waves. What was the subject of our first lecture of the plasma physics course? It's a wave that takes place only in the direction parallel to the magnetic field, for which B0 is parallel to K, which is also parallel to the perturbed electric field. These are the waves that are present in a plasma because the plasma wants to restore the quasi-neutrality, and that are not affected by the presence of the magnetic field. Well, it was nice to retrieve the dispersion relation of the plasma waves. Now let's look at something new that we see here in the determinant of this 2x2 matrix. This determinant can be written as n square minus n square plus epsilon 1, everything squared, minus epsilon 2 equal to 0, epsilon 2 squared. And this is minus n square plus epsilon 1 equal to plus minus epsilon 2, from which we derive that n square is equal to epsilon 1 plus epsilon 2, which is equal to epsilon r. And this will give, as we will see in a few moments, the dispersion relation of the right-handed waves. And epsilon 1 minus epsilon 2, a quantity that we will call epsilon L, and this gives the dispersion relation of the left-handed waves. We have therefore found that there are three families of waves that propagate in the direction parallel to the magnetic field: plasma waves, right-handed waves, and left-handed waves. Let's focus on the last two. First of all, let's look at why they are called in this way, and then what is their dispersion relation. So let's start by looking at the right-handed waves, for which n square is equal to epsilon 1 plus epsilon 2, and we have defined this quantity equal to epsilon r. Now, the equation that we had found that for the wave dynamics says that the n squared, the index of refraction, times k divided by k square minus the identity dyad plus epsilon dot E1 has to be equal to 0. Let's see what the first equation of this linear system tells us about the relationship between the electric field in the different direction. Well, if we look component by component, this linear system tells us for the first equation that minus n theta equal to 0, that minus n square plus epsilon 1 multiplied by Ex minus I epsilon 2 Ey has to be equal to 0, as there is no contribution, no terms related to Ez. This means that Ex will be equal to I epsilon 2 Ey divided by this quantity, minus n square plus epsilon 1. Now we can replace the expression for n squared that we have from here, and this will be equal to I epsilon 2 divided by minus epsilon 1 minus epsilon 2 plus epsilon 1 Ey, which is therefore equal to, simplifying epsilon 1 minus epsilon 1 with plus epsilon 1 will be equal to minus, and then dividing epsilon 2 by epsilon 2, minus I Ey. Well, what does it mean? If we call Ex E, we will have that Ey will be for the right-handed waves equal to I E. Okay, this is a relation in Fourier space. How can it be translated in real space? Well, we will have that electric field will be given by the real part of the electric vector Ex plus I Ey multiplied by the exponential factor that enters in the Fourier mode, I k dot r minus omega t. Now, let's suppose to place ourselves for simplicity in the r equal to 0 location. we will have that the real part of this expression here for r equal to 0 will be given by, for the x direction, by e cosinus of omega t ex plus e sinus of omega t ey. Okay, so let's try to draw what we have just derived mathematically. So we have our 3D coordinates, x, y. The equilibrium magnetic field is in the z direction. The electric field will be in the x line on the xy plane. And the direction of the magnetic field will, on the xy plane, will evolve in time according to the law that we have just derived. In particular, if we draw an angle between the electric field and the x-axis, here, and we call this theta, we see that this theta will be equal to omega t. You see that the electric field rotates in the xy plane in a direction such that by using the right hand rule, well, the direction of rotation coincides with the B0 field. This is why this is called the right-handed wave. Now let's give a look in more details at what is the dispersion relation of the right-handed waves. What we have is that n square is equal to k square c square divided by omega square, which is equal to epsilon r, that is epsilon 1 plus epsilon 2. And then if you substitute the expression for epsilon 1, epsilon 2 that we have seen previously, what you find is that this will be given by omega square plus electron and ion cyclotron frequencies divided by, let me just point in evidence that the sign of omega e, so omega is a negative quantity, to put in evidence is negative sign, we will take the absolute value and put a minus here, and then multiply by omega plus omega cyclotron ions. Well, this expression here can be actually written as, okay, we won't make any change in the denominator. And we will decompose the numerator into the product of two terms, which involves two frequencies, omega r and omega l, which are given approximately. This is why I am using an approximate equal here, by omega r half of the sum of the electron cyclotron frequency plus omega square plus 4 omega pe squared, which is in general a quantity that is greater than omega e, and omega l, which is given by 1/2 minus omega e plus omega e squared plus omega pe squared. And if you look at this, as this is a quantity that is always larger than omega e, this will be always larger than 0. So these omega r or omega l are in practice the solution of the quadratic equation that we have here at the numerator, and which are evaluated in the limit of the electron mass being much smaller than the ion mass. So this is the dispersion relation for the right-handed waves. Now we can derive a similar expression for the left-handed waves by observing that n square is equal to epsilon 1 minus epsilon 2. That is what we have called epsilon L. In this case, we won't do the calculation as we did for the right-handed waves, but let me say that the rotation of the electric field will be in the direction opposite to the magnetic field, B0, and this is why is opposite this is called left-handed waves, and the dispersion relation turns out to be equal to k square c square divided by omega square, and this is equal to upstairs omega plus omega r, omega minus omega L, omega plus the absolute value of the electron cyclotron frequency, and omega minus omega I. We will study the physics of the left-handed waves and of the right-handed waves in the next module. Now let's focus our attention on the waves propagating direction perpendicular to the magnetic field. The waves where the k vector is in the direction of y, and therefore theta is equal to pi over 2. Let's derive the dispersion relation for these waves. Well, for waves propagating perpendicular to the magnetic field, theta is equal to pi over 2, and what we have to evaluate is the determinant of a matrix that is minus n square plus epsilon 1 I epsilon 2 0 I epsilon 2 epsilon 1 0 0 minus n square plus epsilon 3 equal to 0, which can be written as the product of this term here times the determinant of the 2 by 2 matrix up here equal to 0. Okay, here too we have two possibilities. The first one is that minus n squared plus epsilon 3 is equal to 0. This is the ordinary mode. We will denote with OM, for which therefore n squared plus epsilon 3 is equal to 0. In this case, the electric field is again in the direction parallel to B, therefore E is parallel to B0, and well, if you try to evaluate the dispersion relation, you plug the correct expression for epsilon 3, you find that k square c square divided by omega square is equal to 1 minus the sum over the plasma frequency over all species present in the plasma divided by omega square, which is approximately equal to, as the ion plasma frequency is much lower than the electron 1, this is approximately equal to 1 minus omega p e square divided by omega square. This is the so-called ordinary mode that satisfies this first term equal to 0. There is another kind of wave that is present in our system, that is the one for which the second term vanishes. These are the waves that are called the extraordinary mode, XM. So for these waves, epsilon 1 minus n square plus epsilon 1 minus epsilon 2 square has to be equal to 0. For this wave, we will have that Ex and Ey are in general different than 0, but Ez will be constrained to be equal to 0. And if we try to solve the dispersion relation, we will find by expressing n square in terms of epsilon 1, epsilon 2, that n square is equal to epsilon 1 square, epsilon 2 squared, divided by epsilon 1, which we can write as epsilon. Sorry, there is a minus here. It's the difference between epsilon 2 and epsilon 1 squared. And this can be decomposed as epsilon 1 plus epsilon 2 epsilon 1 minus epsilon 2 divided by epsilon 1. And these are two terms that are now familiar to us, and they are called epsilon L and epsilon R divided by epsilon 1. And now these can be written by decomposing this product epsilon L and epsilon R as omega square. It's a few lines of algebra that I spare you. Omega square minus omega R square, omega square minus omega L squared divided by omega square minus omega, we will call LH, and we will give the definition in a few seconds, and omega minus omega square UH. Okay, what are these frequencies that we have just introduced? Omega square UH is given by omega E square plus electron cyclotron frequency plus the electron plasma frequency. And we have denoted it as UH, as we call it upper hybrid frequency. It's a hybrid frequency as it involves both the cyclotron and the plasma frequency. We have also introduced omega LH, and this is equal to omega I, omega E, and then times 1 plus ME over MI, omega E over omega P E squared, divided by 1 plus omega E squared divided by omega PE squared. And this is what we have called lower hybrid frequency. This is the reason of having called it LH. To summarize the content of the present module, well, let me first of all say that we have actually pointed out that the plasma, even within a relatively simple model such as the two-fluid model in the cold plasma limits, well, the plasma is actually a complex medium. It supports, in fact, a large number of intrinsic modes. We have pointed out, in fact, that propagating parallel to the equilibrium magnetic field, there are plasma waves, there are right-handed waves, left-handed waves. Propagating perpendicular to the magnetic field, we have the extraordinary and the ordinary mode. The physical properties of this mode, of these waves, will be the subject of the next module.